Hi everyone, Dr. Burns here with our last lesson on Chapter 5, Ionic and Covalent Compounds. In this lesson, we're going to bring together what we've learned about all of our different compounds and talk about molecular and formula mass, percent composition of compounds, and the molar mass and empirical formulas. I will preface this lesson and say this will be a rather long lesson, only because I have a lot of practice problems available for you to utilize in this video. So while the content isn't much, there's just a lot of practice because practice makes perfect. Now, if you're getting to the point with those practices where you're like, we get it, lady, you don't need to show us every single step, that means one, you're learning it, great, and what you can do then is pause the video, work the problem on your own, and then use my video as a way to check your work, okay? That's the point that we want to get you to so that we are learning all of this information, and that's what we're doing through our practice. For this, you are going to want to have a periodic table present as well as your calculator out. We are going to be doing a lot of calculations today, so you're going to follow along with me while I do some of these calculations about formula mass, molecular mass, empirical formulas, and percent composition. Okay, so let's get started. So some of this we have talked about in previous lessons, but to reiterate, the molecular mass is the mass in atomic mass units, AMUs, of an individual molecule. So to calculate the molecular mass, we have to multiply the atomic mass of each element in a molecule by the number of atoms of that element and then total the masses. So if we wanted to find the molecular mass of water, H2O, we would take the atomic mass of hydrogen and we would multiply it by 2 because there are 2 atoms of hydrogen in that molecule. We would then add to that the atomic mass of oxygen, where we don't need to multiply it by any value because there's only 1 oxygen in our water molecule. So we see that worked out down here, 2 times 1.008 AMUs plus 16 AMUs. And that gives us a molecular mass of 18.02 AMUs. Because the atomic masses on the periodic table are average atomic masses, because we have to take their isotopes into account, the result of such a determination is an average molecular mass. So sometimes this is referred to as the molecular weight. We refer to it in many different ways, but if we're talking about molecular, so individual molecules, that's when we use the unit of AMUs. So although an ionic compound does not have a molecular mass because it's not a molecule, we aren't having actual bonds being formed in an ionic compound, we can use its formula to determine its formula mass, which is the mass of its formula unit. And so we sometimes call this the formula weight. The process to finding the formula mass of an ionic compound is the exact same. We multiply the atomic mass for each element in the formula unit by the number of atoms of that element and then total the masses. So we add it up the same way, they're just referred to as different terms because an ionic compound is not a molecule. A molecule suggests that there are bonds, electrons being shared, which ionic compounds do not form bonds. They are not sharing electrons, they are donating electrons. So let's practice this. For each compound below, identify if it is ionic or covalent, determine its name, and then calculate its molecular or formula mass. So our first example is MgCl2. Mg is magnesium, and Cl is chlorine, which we are going to add IDE to the ending. Now we have to figure out if it is ionic or covalent, because if it's covalent, we have to use our prefixes. If it's ionic, then we don't. So magnesium is a metal, and chlorine is a nonmetal. Therefore, this is ionic, and its name is correct as it is shown, magnesium chloride. We don't use our prefixes for ionic compounds. So now we want to calculate its its formula mass. So look to your periodic table and go to those individual elements and find their individual atomic masses. For magnesium, it has an atomic mass of 24.305 AMUs. We add to that the atomic mass of chlorine, 35.45 AMUs, and we have to multiply that by 2 because there are 2 chlorines. So let me get my calculator out. Okay. So we take 24.305 and we add to that 2 times 35.45. Feel free to type into your own calculator with me, just in case you run past any mistakes. So this would give an average formula mass of 95.205 AMUs. And remember our sig fig rules about this. It's been a while since we've discussed sig figs, but when we're looking at atomic masses and formula masses, we don't want to follow our typical sig fig rules. We just want to leave maybe 2 or 3 decimal places at the very end. And when you're in your ALEKS homework, if it's asking for a mass, it'll tell you how many sig figs it wants. So make sure you pay attention to that as you're practicing in your ALEKS homework. Our next example is P4S7. So phosphorus is P, S is sulfur, so this is 2 nonmetals, meaning this is going to be a covalent compound. So we name this as tetraphosphorus, and 7 is heptasulfide. Okay, so tetraphosphorus heptasulfide, we are now going to calculate its mass. So look to your periodic table, look to those elements, phosphorus and sulfur, and look for their individual atomic masses. On my periodic table, I see phosphorus as 30.97 AMUs, which I'm going to multiply by 4 because there are 4 phosphorus atoms in this molecule. We're going to add to that the atomic mass of sulfur, which on my periodic table I have as 32.06 AMUs. And I'm going to multiply that by 7 because there are 7 sulfur atoms in my molecule. So we can plug that into our calculator. 4 times 30.97 in parentheses. Add to that 32.06 times 7, and we get 348.30. I'm just going to add a 0 at the end to have 2 decimal places. AMUs. So that is our mass for tetraphosphorus heptasulfide. Finally, we have NaNO3. Now, if you remember, NO3 is one of our polyatomic ions. So when we see a polyatomic ion, we automatically know that this is an ionic compound. Okay, and we name our first element first, which is sodium. And then we name our polyatomic ion as is. So NO3, do you remember what polyatomic ion that is? It's nitrate. Okay, we got to remember our ending. ATE is nitrate. Nitrite is NO2. Okay, and nitride would just be nitrogen. So this is nitrate, and it's an ionic compound, sodium nitrate. So when we're doing this, we're now going to find the mass of sodium, nitrogen, and 3 oxygens. So that 3 only applies to this oxygen here. Okay, so let's add that up. Let's look to our periodic table. The molar mass, or sorry, the atomic mass of sodium that I see is 22.99 AMU. And I'm adding to that my atomic mass of nitrogen, which is 14.01 AMU. And to that, I'm taking 3 times the atomic mass of oxygen, which is 16 AMU. So we're going to add that up. 22.99 plus 14.01 plus 3 times 16, and we get a mass of 85. And for sig fig's sake, I'm going to put 2 zeros at the very end of that to show that I have 2 decimal places. Okay, so we have named our compounds, we have found their masses, and identified if they are ionic or covalent. So that really just brings together our entire chapter right here on this one slide. Good job. Let's keep going. So let's calculate the formula mass in AMU for the following compounds. Now these are all ionic compounds, and we know that because we're showing them as their individual ions, which have charges. Okay, and one's a cation and one's an anion. So what we have to do is we have to look at each of these and determine its formula first, and then calculate its formula mass. Because we're not worrying about how much is in this square, we're only worried about how much this and that, the two components of that compound, how much they weigh. So that would be a formula unit. Okay, so we have Rb plus and Cl minus. So those are equal but opposite charges, so they combine in a 1-to-1 ratio. So we get RbCl. So we now take our molecular masses, our formula mass, and we take 85 for Rb, rubidium, 85.468 AMU, plus 35.45 AMUs for Cl. And that gives us a mass of 85.468 plus 35.45, 120.92. We'll just round it out to 2 decimal places, AMUs. Our next step down here is to name them, so let's name it while we're here. This is Rb rubidium. Yep, rubidium. So let's see, R-U-B-I-D-I-U-M, rubidium chloride. Rubidium chloride. Rubidium is in group 1, chlorine is in group 7, so we don't need to show any Roman numerals because it is not a transition metal. Okay, let's try the next one. We have Ba2 plus, barium ion, and Se2 minus, selenium ion. So let's see, they're equal but opposite charges, so we only need one of each. So we have BaSe. Okay, you could also do the crisscross method if that makes you more comfortable. The 2 goes to the selenium, the 2 goes to the barium, you're left with Ba2Se2. We simplify to get BaSe, base. Okay, so we're going to add up our masses for that. Let's do it over here to have some room. The molar mass of barium on my periodic table is 134.33 AMUs, plus my molar mass of selenium is 78.97. So we get a molar or a formula mass of 134.33 plus 78.97. So we get 213.30 for sig figs AMUs. Let's put a name to this. So that's barium, Ba. Barium is in group 2, so no need for a Roman numeral. So we have barium, and Se is selenium. Selenium, so we would make that selenide. So we take off the IUM to make it selenide. Barium selenide. Oh, I spelled that wrong. It's E, not an I. Okay. Now I want you to try this last one. Cd2 plus and O2 minus. Determine first the formula, then the name, and then find the mass. They're in equal but opposite charges, so this would be CdO. Cd is cadmium. Where's cadmium? It's a transition element. So we need to say this is cadmium. And we already know its charge, it's 2. And then this would be oxide. Oops. Oxide, there we go. Okay, let's calculate its mass. So cadmium, I have it as 112.40 AMU. And oxygen has a molar mass of 16 AMUs. So we add those together. 112.40 plus 16 is equal to 128.40 AMUs. Okay, so that's our formula masses for all 3 of those compounds. Let's do a few more. Here are some covalent compounds. So their charges don't matter, and we're not even going to try to name some of these, okay? So what I want you to try to do is calculate the molecular masses in AMUs using the periodic table. So how about you pause the video and try the first 2 on your own. The process for finding these is exactly the same as we did in our previous practice, just we have more atoms to deal with. So for each of these, we're going to take the subscript and we're going to multiply it by its atomic mass. So carbon has an atomic mass of 12.01. I'm going to omit my AMU until the very end just for space purposes, but these have mass units of AMUs. We're going to add to that 6 times the mass of hydrogen, which is 1.01 AMUs, and we'll add to that the mass of 1 oxygen atom, which is 16. So let's take that. 6 times 12.01 plus 6 times 1.01 plus 16. And we get 94.12 AMUs. Up next we have H2SO4. So we're going to take 2 times the mass of hydrogen, 1.01 AMUs, add to that the mass of 1 sulfur, which is 32.06 AMUs, and add to that 4 times the mass of oxygen, 16. So let's do that one. 2 times 1.01 plus 32.06 plus 4 times, oops, that's a division, times 16.00. And we get 98.08 AMUs. Okay, pause the video again and try those last 2 on your own as well. This next one is similar to what we did in our first practice problem. We're just not using oxygen. So we do 6 times the mass of carbon, 12.01, and we add to that 6 times the mass of hydrogen. And we get 78.12 AMUs. And finally, for our last one, we're going to take 6 times the mass of carbon, add to that 12 times the mass of hydrogen, and add to that 6 times the mass of oxygen to get the mass of C6H12O6. So we take 6 times carbon, add 12 times hydrogen, and then add 6 times oxygen, and we get 180.18 AMUs. Okay. For our last set of practice with our molecular masses, let's calculate the molecular mass in AMUs for each of the following compounds. So doing just what we did on our last slide with 3 more examples. So please pause the video again and try these on your own. I encourage you to try these on your own first because we have talked about it before in a previous lecture, and we will be using these types of calculations for the remainder of the semester as well as if you move on to general chemistry too. So I want to make sure that you are as independent in calculating these masses as you can be. Okay, for BCl3, we are going to take the mass of boron, which is 10.81, and add to that 3 times the mass of chlorine, 35.45 AMUs. Get 10.81 plus 3 times 35.45. And we get a mass of 117.16 AMU. For our next one, N2O5, we're going to take 2 times the mass of nitrogen, which is 14.01, and add to that 5 times the mass of oxygen. So we take 2 times 14.01, and we add to that 5 times 16. And we get a mass of 108.02 AMUs. In our last practice problem for this section, we're going to take 3 times the mass of hydrogen. We're going to add to that the mass of phosphorus, which is 30.97 AMUs, and then take 4 times the mass of oxygen. And again, we'll plug that in, 3 times the mass of hydrogen, plus the mass of phosphorus, plus 4 times the mass of oxygen. And we get 98. We'll put 2 zeros after that for sig fig purposes to get a mass of H3PO4 of 98.00 AMUs. Okay, so let's do something with these masses now. Let's talk about percent composition of compounds. So, a list of the percent by mass of each element in a compound is known as the compound's percent composition by mass. So, each compound is made up of multiple different elements, and we can find the percentage that each element takes up in that molecule by finding its percent composition. To do this, we are going to follow this equation here. The percent by mass of a specific element is equal to N multiplied by the atomic mass of the element divided by the molecular mass of the compound overall multiplied by 100. Here, N is the number of atoms of the element in the compound. I'm going to make that CMPD in the compound. The atomic mass is from the periodic table, And the molecular or formula mass we have to calculate using our masses. So just what we were doing before. Those are all of our molecular and formula masses. So we're going to take the number of atoms of each element, multiply it by its atomic mass, divide it by the total mass of the compound, and then multiply it by 100 in order to get a percent. We have to multiply by 100 in order for it to be in terms of percentage. So let's look at an example of that. So let's determine the percent composition of hydrogen peroxide, H2O2. So the first thing that you want to do with all of these problems is determine the molecular mass, because that's the value that you're going to use in the denominator of these problems. So to find the molecular mass of H2O2, of hydrogen peroxide, we're going to take 2 times the mass of hydrogen, add to that 2 times the mass of oxygen. So we'll do that here. And we get that the molecular mass is 34.02 AMUs. Now we want to use the atomic mass of each element to determine the percent composition. So we have to do this for each element in the compound. So let's start with hydrogen. We know that there are 2 hydrogen atoms in this, so N is going to equal 2. So to solve this, we then take 2 times the atomic mass of the element, which is hydrogen, 1.01, divided by the mass, overall mass of the compound, which is 34.02, and then we multiply that by 100. So we take 2 times 1, can't type today, 1.01, and we're going to divide that by 34.02, the mass that we just determined. Now we're not done yet, that's not our final answer. We have to multiply by 100 to make it a percentage. So we have 5.94%. So hydrogen makes up about 6% of hydrogen peroxide's mass. Because it's very small, it's very light, it doesn't take up a lot of space. So it only makes up 6% of hydrogen peroxide's mass. If we look at oxygen, that also has 2 atoms. So N is equal to 2. So now we're going to take 2 times the mass of oxygen and divide it by the total mass of hydrogen peroxide and multiply that by 100. So we're going to take 2 times 16 and divide that by 34.02. And then we multiply by 100. Never forget to multiply by 100. So that gives us a percentage of 94.06%. So oxygen makes up 94% of hydrogen peroxide's mass. It's the heavier of the 2 atoms, so it makes sense that it takes up more of that mass. Okay, so these are the percentages, the percent composition of hydrogen peroxide, of both hydrogen and oxygen in hydrogen peroxide. So we do the part over the whole. Part is how much of that individual atom, over the whole is the total mass. So let's keep practicing. What is the percent by mass of carbon in glucose, C6H12O6? Well, we found that molar mass before, so I'll save that step for you. That molar mass, or that atomic mass, I should say, is 180.18 AMUs. So don't recalculate that. We already calculated it before. So now determine the percent by mass of carbon in glucose. And you have your 4 options there to compare your work to. So from our equation on our previous slides, N in this case is equal to 6 because there are 6 atoms of carbon in this molecule. So we take 6 times the mass of carbon, 12.01, and we divide that by the total mass of glucose, 180.18, and multiply it by 100. So we take 6 times 12.01, the mass of carbon, divide that by our total mass of glucose, and multiply that by 100. So we get 39.993, so let's call that 40%, which is answer A. You could also find the mass percent of both hydrogen and oxygen as well, and you'll know if you're right or wrong if all of those percentages equal 100%, because they all make up that total mass. Okay, let's keep it going. Let's calculate the percent by mass of iron in FeCl3. So the first thing that we want to do is find the mass of iron 3 chloride. This is iron 3 chloride. I'll name things as we go. Okay, so iron 3 chloride, we take the mass of iron, 55.85. We add to that 3 times the mass of chlorine, and we get 55.85 plus 3 times 35.45 and get 162.19 AMUs. So to calculate the percent by mass of iron, we take the mass of iron, 55.85. There's only one of them in the compound. There's only one iron atom, so we don't need to multiply it by anything. You could technically multiply it by 1 if you wanted to. Okay, not going to change it. And we divide it by the total mass of the compound, 162.19 AMUs. So we take 8485, doesn't matter. I typed it in wrong, that's okay. Divide it by 162.19. Multiply that by 100, which I didn't show here. Multiply by 100. And we get a percentage of 34.43%. Next up, let's calculate the percent by mass of carbon in C6H10O4. So what I want you to do is pause this video, calculate the atomic mass of C6H10O4, and then try to find the percent by mass of carbon in that compound. I calculated my mass of C6H10O4 to be 146.16. Okay, I'll skip typing that into our calculator since we've done that so far multiple times. So we then take 6 times the mass of carbon, 12.01, and we divide that by the mass of the compound, 146.16, and we multiply that by 100. So we get 6 times 12.01 divided by 146.16. We multiply that by 100 to make it a percentage. We get 49.30%. So the carbon makes up about half of the mass of this compound. Okay, let's do a few more. Practice makes perfect. If you're getting this concept, feel free to pause the video, practice these on your own notepad, okay, and then use my video as a way to check your work to make sure you did it correctly. So our next example says, tin exists in the Earth's crust as SnO2. Determine the percent composition by mass of both tin and oxygen in SnO2. tin oxide. That's tin 4 oxide. Okay, so the first thing we want to do is find the mass of tin 4 oxide. So we take the mass of tin, which is 118.71, add that to 2 times the mass of oxygen, and we get, let's see, 118.71 plus 2 times 16, we get 150.71. Okay, so now that we know the total mass, we can do tin first, and we take the 118.71. There's only one tin in there, so we don't need to multiply it by anything. We divide it by the total mass of 150.71 and multiply that by 100 to make it a percent. So we take 118.71, divide that by 150.71, multiply it by 100 to get a percent, and we get 78.77%. We can then do oxygen next. So we know that there are 2 atoms of oxygen, so we multiply 2 by the mass of oxygen, and we divide that by the total mass of 150.71. So let's type that into our calculators. Let's divide that by 150.71 and multiply by 100 to make it a percent. And we get a percentage of 21.23%. We can always check our work because 78.77 and 21.23, those percentages equal 100%. Okay, for this next problem, what I want you to do is pause the video and try it on your own. The problem says the anti-caking agent in Morton salt is calcium silicate, CaSiO3. Calculate the percent composition of calcium, silicon, and oxygen in calcium silicate. So we want to do calcium, silicon, and oxygen. We want to find the percentage of each of those in calcium silicate. So pause the video and try that on your own. I got a molar mass of calcium silicate to be 116.17 AMUs. So that's our total that we're going to use for this problem. So for calcium, there's only 1, so we just take the mass of calcium, divide it by our total mass of 116.17, multiply that by 100 to get a percentage. So we get 40.08. Divide that by 116.17, multiply it by 100, and we get 34.50%. For silicon, again, there's just one of them, so we just take its mass, 28.09, and divide it by the total mass of 116.17, multiply it by 100, and we get 28.09 divided by 116.17, multiply by 100 to make it a percent, and we get 24.18%. Finally, for oxygen, there are 3 oxygen atoms in this compound, so we would take 3 times the mass of oxygen, divide it by the total mass of calcium silicate, and multiply it by 100. So we get 3 times the mass of oxygen divided by the total mass of calcium silicate. We multiply by 100 to make it a percentage, and we get 41.32%. And if we added all of those percentages up, we would get 100%, which is just what we would want. Okay. So now that we can find the percent compositions of all of our elements in our compounds, let's talk about the larger scale and talk about molar mass. Now, just like atomic mass, we've talked about molar mass in the past, back in chapter 2, I believe. Okay, and we said that the molar mass of a substance is the mass in grams of 1 mole of a substance. The molar mass of an element is numerically equal to its atomic mass. So whatever we see on the periodic table, that value for mass, it can be used in units of AMUs or in grams per mole. Okay, we can interchange those units. They are exactly the same. So, the molar mass of a compound is calculated in the same way that we calculate atomic mass of a compound. Except we just have to change our units. They're now going to be in grams or grams per mole instead of AMUs. Okay, so 1 mole of water is still equal to 18.02 grams, just like in our previous example where it was equal to 18.02 AMUs. So they are interchangeable. When expressing the molar mass of elements such as oxygen and hydrogen, we have to be careful to specify which form of the element we're talking about. If you recall from our previous discussion of molecules, and specifically elements that exist as molecules, we had 6 on our minds that exist as diatomics. H2, N2, O2, F2, Cl2, and Br2. They all exist in nature as diatomic molecules. So we have to be careful and specify which form of the element we need. So here's some examples here. How many moles of oxygen react with 2 moles of hydrogen to produce water? Well, here we're talking about the reactant of oxygen itself. So this would be molecular oxygen, also known as elemental oxygen. Okay, so oxygen exists predominantly as O2. Okay, that's one of our examples. But we may also mean atomic oxygen as O. So we have to consider the context to tell which form of the element we are using. So when we're talking about oxygen reacting with something, that would be molecular oxygen. It's the oxygen in the air. So it would be O2. And O2 has a molar mass of 32.0, 16 times 2, because there are 2 oxygens in molecular oxygen. How many moles of oxygen are there in 1 mole of water? Well, when we're talking about oxygen being contained in a compound, we're talking about oxygen atom. So we're only talking about 1 oxygen. We're not talking about the molecule of oxygen. So in all of our previous examples, when we've been talking about oxygen and adding it in, we've been using the molar mass of 16 because we're talking about the individual atom of oxygen. Air is approximately 21% oxygen. In that case, we're talking about elemental oxygen, because oxygen exists in our natural world as a gas in the air as elemental oxygen, O2. So we're talking about O2. And many organic compounds contain oxygen. So oxygen is then contained in a compound. Therefore, we are talking about the atom. So we have to be careful about which form of these compounds we are talking about. If you see the word elemental or molecular, we are talking about the diatomic form. If it's contained in something, like contained in a compound, then we're talking about the individual atom. Okay, so now that we can talk about our masses in both AMUs and molar mass, we can now talk about interconverting between mass, moles, and number of particles. And we've looked at this in chapter 2 when we're talking about molar mass of individual compounds or individual atoms, and we were able to convert between mass, moles, and particles using our molar mass as well as Avogadro's number. Okay, so we've done similar problems to this before. We've done this in chapter 2. So let's review this a little. Let's review how we're going to use this conversion chart in order to solve some of our problems. So let's determine the number of moles of CO2 in 10 grams of carbon dioxide. So if we're starting with a mass of carbon dioxide, here we're starting here. If I want to go to moles, in order to do that, I'm going to follow my arrow into moles. So I need to divide by my molar mass. In this case, it would be the molar mass of the compound CO2. So the number of moles of CO2 from 10 grams of carbon dioxide, we have to find the molar mass of CO2 first. So CO2 is equal to the mass of carbon, 12.01, plus 2 times the mass of oxygen. So we get 12.01 plus 2 times 16. This is 44.01 grams per mole. We are now talking about moles in grams, so we have to use molar mass units, which are grams per mole. Okay, so now that we have the molar mass of CO2, we can now take the mass in grams, 10.00 grams, and we do what our conversion chart says, which is to divide by the molar mass. I'm going to set this up so we see how our units cancel. So I'm going to put my molar mass on the bottom and 1 mole on top to show that we're still dividing the two numbers. Okay, we're taking 10 and dividing it by the molar mass, but we can easily see that grams is going to cancel in my equivalency, and I'm going to be left with units of moles. So moles are the only units left. So we take 10, divide it by 44.01, and we get that in 10 grams of CO2, there are 0.2272 moles of CO2. And I'm going to make sure to label everything with both units and with the compound that makes it up. So I also have 4 sig figs here because my original number has 4 sig figs. Okay, let's try another one. Determine the mass of 0.905 moles of sodium chloride. So let's go back to our conversion here. I'm going to erase some of these. Okay, we're starting at moles and we want to get to mass. So if I'm starting at moles, I'm going to follow my arrow to get to mass, and it tells me I need to multiply by my molar mass. Okay, so we need to find the molar mass of sodium chloride. Sodium chloride is NaCl. So this is where remembering our names and being able to turn them into formulas comes in handy. Okay, we have to know how to do that. So sodium chloride is NaCl. We can now find the molar mass of NaCl, which would be NaCl is equal to the mass of sodium, 22.99, plus the mass of chlorine, 35.45, which is 22.99 plus 35.45, oops, hold on, 0.45, there we go. So that is a molar mass of 58.44 grams. Our conversion chart told us that we had to take that 0.905 moles of NaCl and we had to multiply it by the molar mass. So let's show that. I'm going to take the 58.44 grams per 1 mole of NaCl. That should be grams per mole for my units. And you'll see that moles cancel top and bottom, and we're left with units of grams. So we're still multiplying by our molar mass, just like our conversion chart told us to. I'm just showing it in a way that shows the units canceling. So we take 0.905 and we multiply it by 58.44, and we get 52.9 grams of NaCl. Again, that has 3 significant figures because my original number has 3 significant figures. Recall our significant figure rules. Our molar masses are considered constants or having infinite number of significant figures, so we don't use them to determine how many sig figs should be in our final answer. Okay. So what I want you to do now is try this next one. How many molecules of ethane are present in 0.334 grams of C2H6? And now we're looking for molecules. So you're going to have to use Avogadro's number at some point. So use that conversion chart. It should be in your review packet in your lecture guide. Use that to convert between grams of C2H6, which is ethane, to molecules of ethane. If you finish that one, you could also try this next problem, how many molecules are in 9.50 grams of sulfur dioxide. Okay, I calculated my molar mass of C2H6 to be 30.08 grams per mole. So in order to do this, we're going to want to go from grams to moles and from moles to molecules. Okay, so to go from grams to moles, we're going to have to divide by our molar mass. If we look on our chart, that's what it tells us to do. And by doing that, we're going to be left with moles. Once we have moles, we can convert to molecules by multiplying by Avogadro's number. Remember, N sub A is Avogadro's number. Okay, so let's start. We're going to start with our mass, 0.334 grams. And we have to divide by our molar mass. So we put 30.08 grams and 1 mole on top. That way grams cancel and we're left with units of moles. So let's do that. 0.334 divided by 30.08, and we get 0.0111037. Now because this isn't my final answer, I'm not going to round with significant figures. This is now moles. Now that I'm here at moles, I can convert to molecules by multiplying by Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23rd molecules in 1 mole. Okay, 1 mole will always have 6.022 times 10 to the 23rd somethings. In this case, it's molecules. So we put mole on the bottom, so moles cancel, and we're left with molecules, which is the unit that we want to be in. So we take that number of moles, we multiply it by 6.022 times 10 to the 23. And we get 6.69 times 10 to the 21 molecules of C2H6. I have 3 significant figures because there's 3 significant figures in my original problem. Okay, so that's how we find the molecules from the mass. So let's do that again with our second problem here. We have 9.50 grams of sulfur dioxide and we want to know how many molecules there are in that mass. So the first thing we want to do is find the molar mass of sulfur dioxide. So let's take a second and calculate that. I got mine to be 64.06 grams per mole. That's my molar mass of sulfur dioxide. Now we're going to use the same track to get from grams to molecules. We just have to use different molar mass for this problem. So we're going to start with 9.50 grams, and we're going to divide by our molar mass, 64.06 grams per 1 mole. I'm going to cancel out those grams, and we're going to take 9.5, divide it by 64.06, and we get 0.148298 moles. Again, we're not rounding for sig figs yet because this isn't our final answer. After we get to moles, we're going to multiply by Avogadro's number to get to molecules. So just like we did before, 1 mole is equal to 6.022 times 10 to the 23rd molecules. So we take this number, we multiply it by 6.022 times 10 to the 23rd, and we get 8.93 times 10 to the 22 molecules. This has 3 significant figures because there are 3 significant figures in my original problem. So that would correspond with answer number C, answer letter C. Okay. Now let's take this one step further. So this question, I want to know the number of carbon, hydrogen, and oxygen atoms in 1.50 grams of glucose. So this takes a little bit of thinking because in 1 molecule of glucose, which I'm just going to write as GLU, glucose, there are 6 atoms of carbon, there are 12 atoms of hydrogen, and 6 atoms of oxygen. So if I know how many molecules are in 1.50 grams of glucose, I can then use these as conversion factors to find the individual number of atoms of each of those elements in my sample of glucose. Okay, so the first thing that we want to do is determine the molecules of glucose, which is what we just did in our previous examples. We took our molar mass, we took our original mass, we divided it by the molar mass, we then multiplied by Avogadro's number. So let's take a second and let's do that first. Let's determine the number of molecules of glucose. We found the molar mass of glucose before, C6H12O6. This was 180.18. We have the calculation doing that previously. Okay, so we're going to start with our 1.50 grams of glucose, and we're going to divide by our molar mass, 180.18 in 1 mole. Okay, our grams will cancel, and we'll be left with moles, so 1.5 divided by 180. That gives us 0.008325 moles. We then multiply by Avogadro's number just like we did in our previous examples. And we get that in 1.5 grams of glucose there are 5.01 times 10 to the 21 molecules. So if in 5.01 times 10 to the 21 molecules of glucose, if I have 1 molecule of glucose, I know that in 1 molecule there are 6 atoms of carbon. So I can use this equivalency of 1 molecule of glucose has 6 atoms of carbon. Okay, that cancels out my units of molecules and I'm left with units of atoms. So I just take this number and I multiply it by 6, and I get that in 5.0 times 10 to the 21 molecules of glucose, there are 3.00 times 10 to the 22 atoms of carbon. There should be more atoms of carbon than there are molecules of glucose because 1 molecule of glucose is made up of 6 atoms of carbon. So there should be 6 times the amount of atoms of carbon in those molecules of glucose because atoms are smaller than the molecule. This equivalency would also work for the number of atoms of oxygen. So there would also be 3.00 times 10 to the 22 atoms of oxygen. Okay, because these equivalencies are the same, 6 and 6. So let's figure out the atoms of hydrogen. We take 5.01 times 10 to the 21 molecules, and we multiply that by 12 atoms of hydrogen in 1 molecule of glucose. So we take 5.01 times 10 to the 21. We multiply that by 12 to get that there are 6.01 times 10 to the 22 atoms of hydrogen in our sample of glucose. Okay, so we can always take it one step further by using our basic equivalencies that we know about individual molecules and what those subscripts mean in their chemical formula. Okay, so what I want you to do now is try a similar problem. Determine the number of water molecules and the number of hydrogen and oxygen atoms in 3.26 grams of water. So this is exactly what we did in our previous problem. We want to first find molecules of water and then use that to find the individual atoms of hydrogen and oxygen in water, remembering that our water formula is H2O. Okay, so take a second, pause the video, and try out this problem. Okay, so my molar mass of water is 18.02 grams of H2O. We saw that a couple times in our lecture today. Okay, so we're going to use our same pathway to go from grams to molecules. So we're going to take 3.26 grams of water, divide it by its molar mass, 18.02 grams, to get moles. So we take 3.26 divided by 18.02. We get our mole value, 0.18091009, and we're going to multiply that by Avogadro's number. So we multiply that by 6.022 times 10 to the 23, and we get 1.09 times 10 to the 23 molecules. And that has 3 significant figures for our 3 significant figures in our original problem. So now we can think of our equivalency in 1 molecule of water is equal, it has 2 atoms of hydrogen and 1 atom of oxygen. So we can use our number of molecules to find our number of atoms of both hydrogen and oxygen. So we take our 1.09 times 10 to the 23 molecules of H2O. We multiply that by the number of atoms of hydrogen. So there's 2 atoms of hydrogen in 1 molecule of H2O. So that cancels out our units of molecules and leaves us with units of atoms of hydrogen. So we just take that number and we multiply it by 2. So 2.18 times 10 to the 23 atoms of hydrogen. So now we know how many atoms of hydrogen we have. We can now do the same steps, but for oxygen. So we take our number of molecules of H2O, and we use our equivalency that in 1 molecule of H2O there's 1 atom of oxygen. there's no math that we have to do because we're multiplying it by 1. So there's 1.09 times 10 to the 23 atoms of oxygen. Okay, so that answers our question there. Okay, so now that we can convert between moles and molecules and mass, we're now going to use that knowledge to discuss calculating our empirical formulas. So remember, our empirical formulas are the simplest whole number ratio of atoms in a compound. Okay, so we talked about empirical formulas in a previous lesson. If you don't recall that, please go back to that lesson and review it. Okay, so we're going to talk about how those empirical formulas are calculated. So the most common approach to finding the empirical formula is to measure the masses of its constituents. So what makes it up? We have to keep in mind that chemical formulas show the relative numbers, not the specific masses. Okay, so we're just seeing how many of each individual atom make up that compound. So what we can do is we can take the mass amounts of each compound or each atom, and then we can convert it to molar amounts, which we can then use to compute a whole number ratio, because a ratio is just relating two values together. So let's dive deeper into this and let's look at an example. So let's consider a sample that is found to contain 1.71 grams of carbon and 0.287 grams of hydrogen. If we know the mass of an element, then we know the number of moles of that element. Okay, that's what we have our molar masses for on the periodic table. They allow us to convert between mass and moles. Okay, so what we're going to do is take those masses and convert them to mole values, because when we have the mole value, that's going to tell us how many moles of each of those elements is in the compound. So we take the mass value and we divide it by the molar mass in order to convert from grams to moles. So we have our molar mass of carbon and our molar mass of hydrogen, and we get out the mole values of carbon and hydrogen relative to the masses in that sample. So we could show this compound as having a formula of C.142, H.284, but we know that we can't have 0.142 of a carbon atom or 0.284 of a hydrogen atom, because our formulas tell us how many of individual atoms we have. So I can't have half an atom. I can't have 0.142 of an atom. So we need to show this as a whole number ratio. So the ratio is going to relate those two numbers together. So what we're going to do next is we are going to determine the simplest whole number ratio by dividing by the smaller mole value, the smaller subscript, or the smaller mole value. So of our two numbers, carbon had the smallest mole value, so we're dividing carbon's mole value by itself, which gives us a subscript of 1, so C1. And then when I take that mole value of carbon, that 0.142, and divide it by the hydrogen mole value, we get a ratio of 2. Okay, so that's how we're relating these ratios together. So our empirical formula is now CH2, okay, and we have at least one subscript of 1 because it can't be simplified any further, okay? And as we said before with empirical formulas, sometimes the empirical formula and the molecular formula are the same and sometimes they're different. What we're going to explore is first how to calculate these empirical formulas, and then how to determine the molecular formula from the empirical formula. Okay, so the best way to learn this is through examples. So let's do a few examples together. So let's consider a sample that contains 5.31 grams of chlorine and 8.40 grams of oxygen. We want to determine its empirical formula. So we have a little flow chart down here. Okay, we're going to take the mass of our atoms and we're going to divide by their molar masses to find the mole values. Once we have the mole values, we're going to divide by the lowest number of moles to get a ratio. And then we're going to do what we can to convert that to a whole number. Okay, sometimes we may get half values, so we have to then convert to a whole. So we'll look at that in these examples. So the first thing we have to do is convert mass to moles. So we're dividing by the molar mass. So I'm going to take my 5.31 grams of chlorine, and I'm going to divide it by its molar mass of 35.45 grams. And I'm going to do the same thing for oxygen. I'm going to start with 8.40 grams of oxygen. I'm going to divide by its molar mass of 16. We're using 16 because the oxygen is involved in a compound. It's not molecular oxygen, so we're using just the molar mass of oxygen from the periodic table. And that's 1 mole. Okay, so let's determine the mole values for each of these. So we have 5.31 divided by 35.45. We get 0.1497884. We're going to keep as many decimal places as we can because this is not our final answer. We're then going to take 8.40 and divide that by 16. This only gives us 3 decimal places, so we'll use them. Okay, so we're up to here. We found the moles of A and X, so in this case chlorine and oxygen. Our next step is to divide by the lowest number of moles. So these are now mole values. Our molar value for chlorine is smaller than that of oxygen. Okay, we have 0.149 compared to 0.525. Okay, so we're going to divide both of these by 0.1497884. This is going to give us a ratio of 1 for chlorine. And then we're going to take that 0.525 and divide it by 0.1497884. Keep all those decimal places. This gives us a value of 3.5. Now these need to be whole numbers. And what we're not going to do is round at all. We are not rounding. No rounding happens here. We have to multiply to get a whole number ratio. Okay, so what this looks like is we have CL1O3.5. So we have to convert that ratio to the lowest whole numbers. And in order to do that, we're not going to round, we're going to multiply. So what number do we have to multiply this entire formula by to get whole numbers all around? Well, if we have 3.5, we should multiply the whole thing by 2 to get CL2O5, because those are now whole numbers and their ratio is equivalent to the one that it was before. Okay, so this is now a whole number ratio, and this is our empirical formula. Okay, so we're not rounding because we're going to multiply to get our whole numbers. Let's try another one. What is the empirical formula of a compound if a sample contains 0.13 grams of nitrogen and 0.370 grams of oxygen? What is this compound's name? So let's see, we have our plot, or we have our flow chart up here. So our first step is to convert from mass to moles. So we have the masses of each of these. 0.130 grams of nitrogen and 0.370 grams of oxygen. Okay, we have to convert those to molar values. Okay, so we're going to divide by our molar mass. Molar mass of nitrogen is 14.01 grams in 1 mole, and the molar mass of oxygen is 16 grams of oxygen in 1 mole. So we take those, we take 130, divide it by 14.01. We get 0.0092798 moles. And then we take 0.37, divide that by 16, and we get 0.023125 moles. Okay, so now we're going to divide by our smallest mole value. That's our next step. So we've converted to moles. We now want to divide by our lowest number of moles, which is the 0.00927. So we're going to take that, 0.0092798. Divide both of those, 0.0092798. This gives us a ratio of 1, and this would give us 0.0092798. Gives us 2.5. We can round that because we know that 0.49 is going to round to 0.5. If it's within a 100th of a number, you can round it. Okay. So we have our formula as N1O2.5, and just like our previous example, we can't have 0.5s, so we have to multiply this by a number in order to create our whole numbers. Remember, we're not rounding. Okay, so to do that, we're going to multiply by 2, and we get N2O5 as our empirical formula. Our last question is the compound's name. So this would be dinitrogen pentoxide, because there's 5 oxygens and 2 nitrogens. Okay, now I want to make a comment about my not rounding. Okay, so if the decimal is within 0.01 of a whole number, so for example 2.99 and we'll call it 3.01. Okay, if it's within 0.01 of a whole number, then we can round to that whole number. But anything outside of that, so if we're looking at like 2.5, 2.4, 1.7, stuff like that, then that's when we do not round. We have to multiply to a whole number. Okay, so just keep that in mind. If it's super close, like 2.49 or 2.99, 3.01, super close to a round number. So in this case, 2.49 rounded to 2.5, okay? Then you are welcome to round. But if it's something like 2.5, 2.4, 1.7, then we do not round, okay? So keep that in mind when you're doing these problems. Now, we've previously talked about percent composition. Percent composition tells us the percentage that each element makes up in the compound, okay? So an experimentally determined percent composition can be used to determine the empirical formula and even the molecular formula. We just have to make one assumption about those percentages, okay? So we just have to assume that the percentages given are equal to mass values. So for example, let's say for H2O2, so that was the example we did before, H2O2. We said that there was 5.92% hydrogen and 94.08% oxygen. Okay? Now, if we assume a 100-gram sample of H2O2, we know that of that 100 grams, 5.92 grams are going to be hydrogen, and 94.08 grams are going to be oxygen. That's what these percentages are telling us. So when we are given percentages and asked to find the empirical formula, we just take that percentage value and just automatically convert it to a gram. That's all we have to do. You assume if I had 100 grams of that sample, then those percentages would be immediately turned into grams. Okay, so there's no extra work that we have to do. So let's look at an example of that. So a compound containing nitrogen and oxygen is decomposed in the lab, producing 25.93% nitrogen and 74.07% oxygen. Find the empirical formula. So what we're going to do is just say that 25.93% is actually 25.93 grams. Okay, that's all we're going to do. We're just going to change that percentage sign to a gram value. That's it. It's as simple as that. It's a nice assumption that we get to make. The same for oxygen. We can take that 74.07, change that percentage to a gram value. That's all we have to do. You don't need to convert it. You don't need to divide by 100. You don't need to do any of that. You just have to take that percentage and turn it into a G. And that's it. Then you follow the same steps that we were doing before to find the empirical formula. So we take the mass of our atoms, we divide by our molar mass, so this is nitrogen, this is oxygen. I'm going to divide by 14.01 grams is 1 mole. For oxygen, we're going to divide by 16. Okay, we do the same steps. 25.93 divided by 14.01, we get 1.85082. And then we take 74.07, and we divide that by 16, and we get 4.629375. Now again, we're following the same charts. Just because these are whole numbers, don't get confused, don't try to round or anything like that. I oftentimes see students stopping here and rounding. That is not the case. We still want to divide by our lowest number of moles. It just happens to be a larger amount of moles now because we have a larger mass. Okay, so our smaller mole value is the value for nitrogen. So we're going to take 1.85082, divide both of them by that value, and we get 1 here. We're going to divide that by 1.85082, and we get 2.5 again. So we have N1O2.5. Again, that is our formula before we've accounted for whole numbers. So in order to make this a whole number, we're going to multiply by 2 and get N2O5 as our empirical formula, because that's our simplest whole number ratio. I can't leave it at 2.5 because I can't have half an oxygen atom. So we have to multiply to make that a whole number. We are not going to round. Again, not rounding unless we're within 0.01 of a whole number. Okay? So that's how we're converting our ratio to the lowest whole numbers. We're multiplying to get a whole number ratio. Okay, so this one's a little bit trickier, has now 4 compounds in it, but we can use the same assumption that these percentages just turn into grams. So what I want you to do is pause the video and set up this problem and try solving it yourself. So set up each of those conversions to go from percentage to gram, so get rid of that percentage sign, just turn that into a gram, and then convert that grams to moles, and try to find the empirical formula for this compound. Okay, I may run out of room here, so I may have to do this in a couple steps, but that's okay. So let's look at carbon first. So we're starting with 60.86. That percentage is just going to turn into a G. That's all we're going to do. And then we're going to convert it to grams using our molar mass. 12.01 grams of carbon is 1 mole. So we get 60.86 divided by 12.01. We get 5.06744 moles there. Next up, we're going to do hydrogen, 5.83 grams. Again, we're just turning that percentage sign into a G. That's all we have to do. There's nothing else. Okay, we divide that by our molar mass of hydrogen, which is 1.01, 1 mole. So we take that 5.83 and we divide it by 1.01. Get 5.77277. Okay, I'm going to put these over here now. Oxygen is 23.16 grams. Again, just turn that percentage into a G, and that's all you have to do. We're then going to divide it by its molar mass of 16 grams in 1 mole. So 23.16 divided by 16, and we get 1.4475 moles. And our last one is nitrogen, 10.14 grams, divided by its molar mass of 14.11 grams in 1 mole. And we get 10.14, divide that by 14.01 to get 0.723768 moles. Okay. So that brings us up to here. We found all of our moles. We're not done yet. We have to now divide by our lowest number of moles. So looking at each of these, the lowest number of moles is nitrogen. So that's 0.723768 that we're going to divide all of these by. Oops. 0.72, there we go, 37. Too many sevens. Okay, so let's do each of these. Then I'm going to write them down here. So C is 5.06744. This is why we want to keep as many decimal places as possible, because it's going to give us our most precise number. 0.723768. That gives us C7. Okay, 7.0014 can be rounded to 7. Okay, next up we're going to do hydrogen, and that's going to be 5.77277 divided by 0.723768. So 7.97 can be rounded to 8. Next up is oxygen. So we take 1.4475 and divide it by 0.723768. 1.99999 can round to 2. And for nitrogen, it is 1. So we don't have any decimal places, so this is our empirical formula. We can rewrite it to not have the 1 in our end, so C7H8O2N is our empirical formula. Same formula, I just rewrote it. Okay, so hopefully from this problem you can see how the rounding works. Again, if we're super close to a whole number, you can just round it. Trying to take 7.97 and multiplying to get a whole number would take you forever, okay? So it's fine to round stuff like that, okay? So, okay, let's do a few more practice with this. So what I want you to do is pause your video and try these two problems. They are again just using percent composition to find the empirical formula. Okay, again this one is just 2 atoms for each of these, so it's a little bit simpler than the examples that we just did. So please pause your video, try these two problems, and then come back and check in on our answers when you're done. So we start these problems off exactly how we did our previous ones. We're going to take those percentages and just turn them into grams. So we're going to take that 59.66%. We're going to turn that into grams, and this is of chlorine. So we're just going to divide by its molar mass, 35.45 grams of Cl is in 1 mole. For oxygen, it's the same thing, 40.34 grams of oxygen. We just take that percentage and turn it into a grams. We divide it by its molar mass of 16 grams. Okay, so let's do some math here. 59.66 divided by 35.45, and we get 1.682937. Keep as many decimal places, because the more decimal places you get, the more precise your number is going to be and the less questions you're going to have about your rounding. Okay, so then we take 40.34 and we divide that by 16, and we get 2.52125. Our next step is to then divide by our smallest mole value, which is the 1.68. So we take 1.68, 29337, divide both of those, 1.68, 29337. So that gives us 1 for chlorine. We divide that by 1.682937, and we get 1.49, which we can round to 1.5. That's fine. So we get CL1O1.5. So that's our original formula, but we know we can't have any decimals, so we have to multiply this by 2 to get a whole number. So we get Cl2O3 as our formula. That's our empirical formula. For our last problem here, we're doing the same thing. We are taking those percentages, 57.14, and we're just turning those into grams. This is of sulfur. So we're going to divide that by its molar mass. 32.06 grams of sulfur is in 1 mole. And for oxygen, we're doing the same thing. 42.86% turns into grams of oxygen. And in 1 mole of oxygen is 16.00 grams. So we take those values, divide them by their molar mass, 32.06. Gives us 1.782283. Lots of decimal places, keep them around. 42.86. Divide that by 16 equals 2.67875. Keep as many decimal places as you can. We divide by our smallest mole value, which is 1.782283. 1.782283. This gives us a 1 for sulfur, and for oxygen we just have to divide 1.782283. We get 1.5. So we have S1O1.5, which is our original. We have to multiply this by 2 to get a whole number, so we get S2O3 as our empirical formula. Okay, let's try one more before we move on to our next portion of finding the molecular formula using similar practice. So, what is the empirical formula of a compound that is 25.26% carbon, 14.74% nitrogen, and 60% fluorine? So pause the video and try this one on your own. Okay, So we're going to start this off like we do all of our other problems. 25.26% turns into grams, which we're going to divide by the molar mass of carbon. It's 1 mole. Nitrogen, the same thing, 14.74% turns into grams of nitrogen. Divide that by its molar mass of 14.01 grams in 1 mole. And finally, 60.0% fluorine becomes grams of fluorine, which we divide by its molar mass of 19. Okay, so we take 25.26, divide that by 12.01. We get 2.103247 moles. Next up is nitrogen. We get 14.74. Divide that by 14.01. 1.0521056 moles. And finally, we take fluorine, 60.01, divide that by 19, and we get 3.1578947 moles. Okay, we're not done yet. We have to divide by our mole value. So we're going to take that, divide by our smallest mole value, which is 1.0521056, 0.0521056, 1.0521056. So that gives us 1 for nitrogen. For fluorine, that is 1.0521056. 3.00 is 3. And for carbon, we get 2.103247 divided by 1.0521056. 1.9999 rounds to 2. So this formula is then C2NF3. That is our empirical formula for this compound. Okay, so now that we have mastered finding our empirical formulas from both mass values and percent compositions, we're going to take this one step further and talk about how we can now find the molecular formula from that empirical formula. So the molecular formula can be derived from the empirical formula using the expression using the molecular mass and the empirical formula mass. The ratio between those values gives us a value of n, gives us a whole number. Okay, because if we remember back to when we were talking about empirical formulas and molecular formulas, we could simplify our molecular formula by dividing by the least common denominator. Okay, that value that we divide by is now the n value that we're finding here, and we're going to be multiplying by our empirical formula by to find the molecular formula. Okay, so they're all related by whole numbers because it's just a ratio that we're changing it on. So what we're going to do is take the molecular mass, or the molar mass, divide it by the empirical mass, and that's going to give us a whole number ratio. That whole number is then going to be used to multiply the entire empirical formula by to create the molecular formula. Okay, so the best way to show this is through practice. So let's keep practicing. So we want to determine the empirical formula of a compound that is 30.45% nitrogen and 69.55% oxygen by mass. Given that the molar mass of this compound is approximately 92 grams per mole, let's determine the molecular formula of the compound. So the first thing we have to do is find the empirical formula. That is our first step. We can't find a molecular formula without the empirical formula. So let's take our percentages, and we're going to do our steps like we were doing before. So we're going to take 30.45%, turn that into grams, that's nitrogen. And we're going to divide that by its molar mass. And we're going to do the same thing for oxygen, 69.55 grams of oxygen, divide that by its molar mass. Okay, so we're starting off just like we did in our previous examples, no different. 30.45, divide that by 14.01, and we get 2.17344475. We're going to take 69.55, divide that by 16, and we get 4.346875. We divide by our smallest mole value, which is that 2.17. This is all the same thing that we did before in our previous examples. And we get 1 and 2 as our empirical formula. So our empirical formula is NO2. Now, to find the molecular formula, we have to take the molecular formula and divide it by the empirical formula mass. So we know that this compound has a molar mass of 92 grams per mole. So we're going to take 92 grams per mole and divide it by the empirical formula. Empirical formula mass. We just have to find that empirical formula mass first. So nitrogen, there's one nitrogen, so it's 14.01 grams plus 2 times 16. Right? That's how we find our molar mass. That's what we did in all of our previous practice problems earlier in this lesson. Okay, so we take 14.01 plus 2 times 16. So the empirical formula mass is 46.01. So I take that 92, I divide it by 46.01, and this is going to give me a whole number, or approximately a whole number. 92 divided by 46.01 gives me 1.999. We're going to use our same rounding rules that rounds to 2. Now what we're going to do is use that 2, say that NO2, the empirical formula, needs to be multiplied by a factor of 2 to get the molecular formula. So that would then be N2O4. So the empirical formula is NO2. The molecular formula is N2O4. And you can always double check that by finding the mass of that molecular formula. So we take 14.0, multiply it by 2, add together 4 times 16. So let's do that. 2 times 14.01 plus 4 times 16. And we get 92.02, which is pretty dang close to 92 grams per mole. So our molecular formula is N2O4. It can be simplified to an empirical formula of NO2, which is what we did in our previous lesson when we were talking about empirical formulas. Let's try another practice. So let's determine the molecular formula of a compound with the empirical formula CF2 and the molar mass of 200.04 grams per mole. So the problem did the hard work for us. It found the empirical formula. So what we have to do is first find the empirical formula mass. So we have carbon, 12.01 grams per mole. And we're going to add to that 2 times the mass of fluorine, 19. Okay, so we take 12.01, we add to that 2 times the molar mass of fluorine, and we get an empirical formula mass of 50.01. We now take that molecular mass, the molar mass here, we take it and divide it by the empirical formula mass to see how many empirical formulas make up the molecular formula. If you want to think about it that way, how many times can I fit how many times can I fit my empirical formula into my molecular formula? So 50.01. So we take 200.04, divide it by 50.01, and gives us an N of 4. So that 4, we then say we take our empirical formula, which was CF2. We have to multiply that by 4. Okay, so that gives us C4F8. So this is our molecular formula. and CF2 is our empirical formula. So we're just finding the ratio between their masses to determine what factor we have to multiply the empirical formula by to get the molecular formula. Okay, let's do another one. Calculate the molecular formula of a compound with the empirical formula C2H2O and a molar mass of 132.12 grams per mole. So our first step is to find the molar mass of our empirical formula. So we have 2 times the mass of carbon, and we're going to add to that 2 times the mass of hydrogen, and add to that the mass of oxygen. So calculating the mass just like we do for any formula that we're given, which we practiced multiple times earlier in this lecture. So we take 2 times the mass of carbon, add to that 2 times the mass of hydrogen, and then a mass of oxygen. So our empirical formula mass is 42.04. So we now take our molar mass, our 136.12, divide that by 42.04. Okay, that's going to tell us how many empirical formulas fit into our molecular formula. So we get 136.12 divide by 42.04, and we get, okay, I think I have a typo. I think this should be 126.12. So make that correction in your lecture pack. That should be 126.12. I think I typed that wrong. I'm sorry. So we take our 126.12 and we divide that by 42.04. 126.12, divide that by 42.04, and we get a factor of 3. Okay, so we now take our empirical formula, which was C2H2O, and we multiply that by a factor of 3 to get a molecular formula of C6H6O3. Sorry about that typo. Okay, so let's bring it all together. Let's do this in a 2-step process. The first thing that we're going to do in this problem is we are going to use our percent composition knowledge and find the empirical formula. Once we find the empirical formula, we are then going to use that to find the molecular formula. So we did a similar problem to this when we first introduced molecular formulas. Okay, we've practiced a lot with percent composition and finding empirical formulas. So let's bring together all of our knowledge and let's try this problem. And I want you to first try it on your own because I want you to get confused and I want you to get stuck and I want you to come back to this video so that you can get unstuck and learn this even more. Okay, so pause the video, try this problem, go through and find the empirical formula just like we did in the previous portion of this lecture. Then use that empirical formula to try to determine the molecular formula, given that the molar mass is here on the screen. Okay, let's do our first step of finding the empirical formula. We're going to take our percentages and turn them into masses. So 52.14% becomes a gram. We're dividing that by our molar mass. That's carbon. I'm going to label that as carbon. Here's hydrogen. We get 13.13 grams of hydrogen. Divide that by its molar mass. And finally, we have oxygen, 34.73. We're just turning those percentages into grams. 16.0 grams for 1 mole. Okay, let's do some math. 52.14 divided by 12.01. We get 4.34138. Then we take 13.13, divide that by our mass, we get 13. Let's throw some decimal places on there just for sig fig purposes. And let's do oxygen. 34.73 divided by 16. We get 2.170625. Okay, we divide by our smallest mole value, which is 2.170625. 2.170625. 2.170625. So that gives us 1 for oxygen. 13 divided by 2.170625 there. That gives us 5.98. That can round up to 6. And for carbon, we get 4.34138 divided by 2.170625. And that is 2. So our empirical formula is C2H6O. That is our empirical formula. Now we want to find the molecular formula, so we need to first find the empirical formula mass if we're going to compare them. So we take 2 times the mass of carbon, add to that 6 times the mass of hydrogen, and add to that the mass of oxygen. So we get 2 times 12.01 plus 6 times the mass of hydrogen, 1.01, plus 16. Our empirical formula mass is 46.08 grams per mole. Now to calculate our ratio, we're going to take our molar mass, 138.204, and divide that by 46.08. So we're going to take 138.204, divide that by 46.08, and we get 2.999, which we can round to 3. So we're going to take that empirical formula, C2H6O3, multiply, that should just be an O, multiply that by a factor of 3, which gives us C6H12O3 as our molecular formula. Okay. Let's keep it going. So, a compound consists of 20.32 grams of carbon, 5.12 grams of hydrogen, and 7.19 grams of nitrogen. We're going to follow the same steps, find the empirical formula first, and then determine the molecular formula given the molar mass. We're going to start this problem out similar to how we did our previous empirical formula problems. These are not percentages, these are masses, so we can just convert these masses to moles, just like we have been doing. So we're going to take 20.32 grams of carbon, and we're going to divide by our molar mass. We're going to take 5.12 grams of hydrogen and divide by its molar mass, and 7.9 grams of nitrogen. Divide by its molar mass, 14.01. Okay, 20.32 divided by 12.01 gives us 1.69192339. We'll just leave it at 33. Keep a lot of decimal places. We're going to take 5.12. Divide that by 1.01, and we're going to get 5.069306, and we're going to take 7.9 and divide that by 14.01 to get 0.563889. We divide by our smallest moles, which is our value of nitrogen, so 0.563889. 0.5638829. We know that's going to give us a nitrogen of 1. Hydrogen, we're going to get 5.069306 divided by 0.5638829. 8.98999, we can round that to 9 for hydrogen, and for carbon we get 1.6919233 divided by that 0.5638829, and we get 3.00. So our empirical formula is C3H9N. So to determine the molecular formula, we have to compare the molar mass to the empirical formula mass. So we have to find the empirical formula mass. So we take 3 times the molar mass of carbon, add to that 9 times the mass of hydrogen, and add to that the mass of nitrogen, which is 14.01. So to find the molar mass of our empirical formula, we do 3 times 12.01 plus 9 times 1.01 plus 14.01. We get a mass of 59.13 grams per mole. Okay, so now we're going to take that molar mass, that 236.448, and divide it by 59.13. So we take 236.448 divided by 59.13. We get 3.998, which we can round to 4. So we take that C3H9N, we multiply it by a factor of 4 to get C12H, what's 9 times 4? Double check my math there. 36N4. Okay, so that is our molecular formula. And remember, we can always check our work by comparing the mass of what we get for a molecular formula to what was given in the problem, just to make sure we don't have any errors. Okay, I think we have 3 more problems left, so let's really end this lesson with showing our knowledge, proving to ourselves that we know this. So let's calculate the molecular formula of a compound whose molar mass is 410 grams and has an empirical formula of C2H3N. So we already know our empirical formula, so we can find the mass. We're going to do 2 times the mass of carbon plus 3 times the mass of hydrogen plus the mass of nitrogen. So just like we were doing before in finding our molar masses, our empirical formula mass is 41.06. So we're going to take that 410, divide it by 41.06. So 410 divided by 41.06 gives us 9.98, which we can round to 10. So we're going to take C2H3N, we're going to multiply it by a factor of 10 to get a molecular formula of C20H30N10. That is our molecular formula. Okay, you pause the video, try this problem on your own. Let's find the molecular formula from these percent compositions and the molar mass of 171 grams. Finish this one, prove it to yourself that you know it, and then we can move on to our very last problem of this lesson. Okay, we're going to start this off just like we do our regular percent compositions. Those percentages turn into gram values. So we have 63.16 grams, and we're going to divide it by its molar mass. That's carbon, I'm going to label it. Same thing for hydrogen. Divide by its molar mass. And for oxygen, 28.07. Divide by its molar mass. Okay, so we take 63.16, divide it by 12.01. We get 5.2589508. Oops, that is not written clearly. Let's make that a little bit neater. 5.2589508. There we go. For hydrogen, we get 8.77 divided by 1.01. 8.683168. And for oxygen, 28.07 divided by 16 gives us 1.754375. Divide by our smallest mole value, which is the oxygen, 1.754375. 1.754375. That gives us 1 for oxygen, 8.683168 divided by 1.754375. We get 4.94. We'll round that up to 5. And 5.2589508 divided by 1.754375. We get 2.99, so we'll round that to 3. So our empirical formula is C3H5O. We can find our molar mass of that, 3 times 12.01 plus 5 times 1.01 plus 16. That's 57.08. So we take 171 divided by 57.08. We get 2.99, which we round to 3. So we're going to take that and multiply it by a factor of 3 to get C6H15O3 as our molecular formula. Okay, last problem here. This one's talking about caffeine, probably what you had to drink to get through this lecture. Caffeine is a stimulant found in coffee, and it contains 49.5% carbon, 5.15% hydrogen, 28.9% nitrogen, and 16.5% oxygen by mass. And it has a molar mass of 195 grams per mole. Calculate its molecular formula. Pause your video, do this problem, get it 100% correct. Join me back here to show that you got the right answer. Since we're using percentages, those percentages just become grams. So 49.5% becomes gram of carbon, divide by its molar mass. For hydrogen, 5.15 grams of hydrogen, divide by its molar mass. For nitrogen, 28.9 grams of nitrogen becomes, we divide by its molar mass. And 16.5% becomes grams of oxygen, and we divide by its molar mass. So now we calculate our mole values, 49.5 divided by 12.01, and we get 4.1215653. Then we do hydrogen, 5.099099. Keep a lot of decimal places. Remember, we're not rounding at any point. 28.9 divided by 14.01. And we get 2.062812 and 16.5 divided by 16 is 1.03125. Divide by our smallest mole value, which is the oxygen. So that gives us 1 for oxygen, 2.062812 divided by 1.03125. That gives us 2 for nitrogen. Hydrogen is then 5.099099 divided by 1.03125. 4.9, we can round that to 5. And 4.12156653, divide that by 1.03125. 3.99 can round to 4. So we have C4H5N2O. If we have a molar mass of 195, we need to divide it by our empirical formula mass, which we can find this way. So I'm taking 4 times 12.01, adding that to 5 times 1.01, 2 times the mass of nitrogen, and 1 oxygen, so 97.11. Oops, 97.11. 195 divided by our answer gives us 2.0. So we're going to take that and multiply by a factor of 2 to get C8H10N4O2 as our molecular formula. And that was our last problem of this lecture. And through this lecture, we talked about molar masses, molecular masses, finding empirical formulas through mass ratios, percent composition, and empirical formulas. So we did a lot of practice, and you're going to do a lot of practice in your ALEKS homework as well, but you are going to crush it.